April 7th, 1945. 30,000 feet above the Pacific Ocean, somewhere between Iwo Jima and the Japanese home islands. Major James Tapp checked his fuel gauges for the 14th time in an hour, watching the needles hover at numbers that would have seemed suicidal 6 months earlier. His North American P-51D Mustang, tail number 44-63474, vibrated with the steady rhythm of its Packard V1650-7 engine, the American-built version of the legendary Rolls-Royce Merlin that had broken the Luftwaffe over Europe. Behind him stretched 90 more Mustangs of the 15th and 21st Fighter Groups, their aluminum skins catching the early morning sun as they climbed toward a rendezvous point that military planners had once considered beyond the realm of possibility. 750 miles of open ocean separated Iwo Jima from Tokyo. 750 miles of featureless water with no landmarks, no emergency airfields, no margin for error. A single-engine fighter attempting such a journey would have been considered a suicide mission as recently as 1943. Yet here they were, 91 P-51Ds approaching the sacred airspace of the Japanese home islands, carrying enough fuel to fight for 2 hours over the target and return safely to base. The mathematics that made this possible represented nothing less than a revolution in air warfare, a triumph of engineering over geography that would shatter Japanese strategic calculations in a single morning. Through his bubble canopy, Tapp could see Mount Fuji emerging from the morning haze, its snow-capped peak unmistakable against the clear spring sky. The sacred mountain that had inspired centuries of Japanese art now served as a navigation waypoint for American fighter pilots. The symbolism would not be lost on either side. Below, the patchwork of rice fields, villages, and military installations spread across Honshu had never before seen American fighters. Carrier-based Navy aircraft had struck Japan, but they came from ships that could approach no closer than a few hundred miles. These were land-based Army Air Force fighters, operating from a volcanic island captured barely 6 weeks earlier, demonstrating capabilities that Japanese commanders had assured their pilots were physically impossible. The P-51D Mustang that carried Tapp toward Tokyo represented the culmination of a remarkable international collaboration. The aircraft's origins lay not in American requirements, but British necessity. In 1940, the Royal Air Force had approached North American Aviation with an urgent request for fighters, specifying delivery times that made using existing American designs impractical. North American's chief designer, Edgar Schmood, promised to deliver a prototype in 120 days. He delivered in 117, creating an airframe so aerodynamically advanced that it would eventually outperform every fighter in the American inventory. The original NA-73X featured a revolutionary laminar flow wing that Schmood had developed from theoretical research conducted at the National Advisory Committee for Aeronautics. Traditional airfoils created turbulent airflow almost immediately as air passed over the wing surface, generating drag that consumed fuel and limited speed. Schmood's design maintained smooth, laminar airflow over a much greater percentage of the wing chord, reducing drag by approximately 35% compared to conventional fighters. The fuel savings proved enormous, the speed gains significant, but the early Mustang suffered from a critical limitation that nearly doomed the program. The Allison V1710 engine, powering the first Mustangs, delivered adequate performance at low and medium altitudes, but lacked the supercharging necessary for high-altitude operations. Above 15,000 feet, the engine's single-stage supercharger couldn't compress enough thin air to maintain power. The Mustang's beautiful airframe was hobbled by an engine that gasped for breath precisely where modern air combat occurred. The aircraft that could have changed the air war languished in ground attack roles, its potential unrealized. The transformation came from an unlikely source. In April 1942, Rolls-Royce test pilot Ronald Harker flew an early Mustang and immediately recognized what others had missed. The airframe was exceptional, limited only by its power plant. Harker's recommendation to mate the Mustang with the Rolls-Royce Merlin 61 engine, featuring a two-stage, two-speed supercharger with intercooler, would create one of history's most successful aircraft marriages. By October 1942, a converted Mustang flew with the Merlin engine, reaching speeds that shocked even optimistic observers. The aircraft that had struggled above 15,000 feet now maintained full power at 30,000 feet and beyond. The Packard Motor Car Company received contracts to license-build the Merlin in America, eventually producing the V1650-7 that powered the P-51D. This engine delivered 1,490 horsepower at takeoff, rising to approximately 1,720 horsepower with water methanol injection at emergency war power settings. The two-stage supercharger maintained sea-level manifold pressure at altitudes where Japanese engines produced barely half their rated power. The first stage compressed the thin, high-altitude air, then passed it through an intercooler to reduce temperature, before the second stage compressed it further. The result was dense, oxygen-rich air delivered to the cylinders at altitudes where enemy fighters wallowed helplessly. The specifications that emerged from flight testing at Wright Field established the P-51D as perhaps the finest propeller-driven fighter ever produced. Maximum speed reached 437 miles per hour at 25,000 feet. Service ceiling exceeded 41,000 feet. Rate of climb surpassed 3,400 feet per minute at sea level. But the statistic that mattered most for Pacific operations appeared in the range column. 2,080 miles with external drop tanks, enough to escort bombers from England to Berlin and back, or from Iwo Jima to Tokyo and home again. The fuel system that made such ranges possible reflected careful engineering optimization. Internal fuel capacity of 269 gallons, distributed between fuselage and wing tanks, provided the foundation. Two 110-gallon drop tanks beneath the wings added another 220 gallons for long-range missions. The Merlin's exceptional fuel efficiency at cruise settings, consuming approximately 65 gallons per hour at economical power, stretched every drop of the 489-gallon total load. American pilots learned to nurse their aircraft across vast distances, climbing gradually to altitude, leaning their mixtures to the edge of detonation, and trusting their engines to carry them through. At 0700 hours on April 7th, the formation of P-51Ds reached their rendezvous point with 107 Boeing B-29 Superfortresses of the 73rd Bomb Wing. Captain Arthur Bridge of the 45th Fighter Squadron later described the spectacle in his combat report. The massive bombers circling in a grand assembly pattern, their aluminum skins reflecting sunlight like a school of silver fish. Their four Wright R-3350 engines, each producing 2,200 horsepower as they climbed toward bombing altitude. The rendezvous itself represented a triumph of navigation and planning that demonstrated American organizational capabilities at their peak. The fighters had flown 750 miles over featureless ocean, navigating by dead reckoning, basic radio compass, and precise timing, arriving within minutes of the scheduled meeting. The first Japanese interceptors appeared as the combined formation crossed the coast of Honshu. More than 100 fighters scrambled from airfields around Tokyo, a mixed force representing nearly every operational type remaining to Japanese air defenses. Nakajima Ki-84 Hayates and Ki-43 Hayabusas from Army units joined Kawasaki Ki-61 Hines and Ki-44 Shokis. Navy fighters included Mitsubishi A6M Zeros and the new Kawanishi N1K2J Shiden Kai. Japan's attempt to counter the American advantage with a more powerful design. The pilots climbing to meet the American formation represented Japan's last organized air defense, a mixture of veterans who had survived 3 years of attrition and replacements whose training had been cut short by fuel shortages and operational necessity. The shock that Japanese pilots experienced upon identifying their opponents would reshape their understanding of the war's strategic reality. These were not carrier-based Navy fighters with limited range and endurance. These were land-based Army Air Force fighters that had somehow materialized over the Japanese homeland from bases that every calculation showed were impossibly distant. Flight Sergeant Totani Mizu, flying a Ki-84 with the 56th Sentai, later recounted his disbelief in post-war interviews. When his unit scrambled, controllers reported enemy fighters approaching Tokyo. The pilots assumed the report was in error, that controllers meant enemy bombers. When Totani Mizu saw the Mustangs with his own eyes, their distinctive bubble canopies and low-drag radiator housings unmistakable, he thought he must be dreaming. Japanese commanders had repeatedly assured their pilots that no American fighter could reach Japan from island bases. Yet there they were, dozens of them, flying formation as if they owned the sky. In that moment of recognition, Totani Mizu understood what his superiors would not admit. The war was truly lost. If American fighters could appear over Tokyo, then no point in the empire remained safe. The mathematics of distance that had protected Japan for centuries had been overcome by engineering that Japanese industry could no longer match. The engagement that followed demonstrated the technological gulf between the two air forces in brutal clarity. American pilots dropped their external tanks as Japanese fighters approached. The empty aluminum containers tumbling earthward, some exploding on impact, others bouncing across rice paddies. Freed of the drag penalty, the P-51Ds accelerated to combat speed, their Merlins singing at full power. The initial contacts occurred at 25,000 feet, the altitude where the Mustang's advantages proved most decisive. Major Tapp, leading his flight into the first wave of Japanese interceptors, observed patterns that would repeat throughout the engagement. The Japanese came in their traditional 3-aircraft Shotai formations, but their coordination appeared poor. Flight leaders would commit to attacks while wingmen failed to follow through, their timing erratic, their approaches predictable. Whether from fuel shortages, ammunition conservation, or simple inexperience, the Japanese response lacked the aggressive precision that had characterized their early war operations. The P-51Ds dove through the formations with a speed advantage approaching 100 miles per hour, fired quick bursts, and zoom climbed back to altitude before defenders could react. The tactic exploited every advantage the Mustang possessed. Superior dive speed that approached 500 miles per hour without control problems. A zoom climb rate the Japanese aircraft couldn't match with engines struggling in thin air. And the energy retention that the laminar flow wing provided. American pilots described it as shooting fish in a barrel, though the analogy obscured the years of training, engineering development, and industrial mobilization that made such dominance possible. The armament carried by the P-51D reflected American combat philosophy developed through 3 years of air warfare. 6 Browning AN M2 50 caliber machine guns, 3 mounted in each wing, delivered devastating firepower with exceptional reliability. The early P-51Ds carried 500 rounds for each inboard gun and 270 rounds for the center and outboard positions, providing a total ammunition load of 1,880 rounds. Later variants standardized at 400 rounds per inboard gun, reducing total capacity to 1,880 rounds, but improving feed reliability in high-G maneuvering. Either way, American pilots possessed ammunition supplies that dwarfed their opponents. Each M2 Browning fired at a cyclic rate of approximately 800 rounds per minute. 6 guns, firing simultaneously, delivered 4,800 rounds per minute of concentrated firepower. 80 armor-piercing incendiary rounds striking the target area every second. The 50 caliber round weighed 46 grams and traveled at 2,900 feet per second, delivering kinetic energy sufficient to penetrate aircraft armor, ignite fuel tanks, and destroy engines with a few well-placed hits. The ballistic characteristics were so well understood from years of training that American pilots could reliably engage targets at 400 yards, adjusting instinctively for deflection and range. When the smoke cleared and the surviving American fighters turned for Iwo Jima, the 7th Fighter Command claimed 21 Japanese aircraft destroyed, with additional probables and damaged. American losses totaled 2 P-51Ds, with 1 pilot rescued by lifeguard submarine. The exchange ratio exceeded 10-1. A dominance that would only increase as American pilots gained experience over Japan and Japanese pilot quality continued its fatal decline. The return flight stretched across 6 hours of ocean navigation, each pilot monitoring fuel gauges that crept toward empty, calculating ground speed against remaining distance, trusting instruments and training to bring them home. The magnetic variation between Iwo Jima and Tokyo was approximately 3 degrees west, a fortunate geographic coincidence that simplified navigation. A pilot who became disoriented in combat or weather could simply fly south-southeast, knowing that eventually the distinctive cone of Mount Suribachi would rise from the ocean ahead. Assuming he had enough fuel, assuming his engine held together, assuming he remained conscious through 8 hours strapped into a cramped cockpit, unable to stand, unable to stretch, relief tube freezing at altitude. The physical strain of very long-range missions imposed demands that tested human endurance as severely as any combat. Pilots dealt with cramping legs, numb buttocks, hypnotic fatigue from hours of featureless ocean, and the constant anxiety of flying a single-engine aircraft over water, where mechanical failure meant almost certain death. The cockpit ergonomics of the P-51D, refined through years of combat feedback and thousands of pilot reports, helped mitigate, but could not eliminate, the punishment. The bubble canopy provided 360-degree visibility. The seat adjusted for pilots of different heights. The rudder pedals moved to accommodate different leg lengths. Instruments arranged logically, with airspeed, altitude, and engine gauges directly in the pilot's line of sight. But nothing could make 8 hours in a fighter cockpit comfortable. The aircraft that landed at Iwo Jima, as sunset painted the Pacific in shades of orange and red, had proven what skeptics considered impossible. Single-engine, fighters could operate at ranges exceeding 1,500 miles round trip. They could engage the enemy over his homeland, provide effective escort for strategic bombers, and return safely to base. The very long-range capability that brought Mustangs to Tokyo represented a revolution that changed the fundamental mathematics of Pacific air warfare. Japanese commanders receiving reports of the engagement understood the strategic implications immediately. The distance that had protected Japan since the Mongol invasions had been overcome. American industrial capacity, expressed through an aircraft that combined British engine technology with American aerodynamic innovation, had rendered geography irrelevant. Every assumption underlying Japanese defensive strategy required revision. In cockpits across the decimated Japanese interceptor force, surviving pilots processed what they had witnessed. The Americans had come from impossibly far away, fought with overwhelming superiority, and departed with minimal losses. They would return tomorrow, and the day after, and every day until Japan surrendered or ceased to exist. The shock of American fighters over Tokyo was not merely tactical surprise. It was the physical manifestation of industrial capacity that Japan could never match, technological superiority that no amount of warrior spirit could overcome, and strategic reach that made the Japanese homeland as vulnerable as any Pacific island. The P-51D Mustang flying over Mount Fuji on the morning of April 7, 1945, represented something more than an aircraft. It embodied the accumulated advantage of nations that had invested in engineering excellence, mass production, and logistics systems capable of projecting power across oceanic distances. The laminar flow wing that reduced drag by 35%. The Merlin engine that maintained power at 30,000 feet. The drop tanks that extended range beyond anything Japanese planners had imagined possible. Each element represented years of research, development, and industrial refinement that Japanese industry, under constant bombardment and starved of resources, could no longer replicate. The pilots who flew those first missions over Tokyo understood they were making history, though few could articulate exactly why. They knew their aircraft was exceptional, their training superior, their logistics support unprecedented. What they couldn't fully grasp was how completely the balance had shifted, how thoroughly American industrial warfare had overwhelmed Japanese martial tradition. That understanding would come later, in the mounting kill ratios, the collapsing Japanese resistance, and the eventual silence over airfields where no defenders rose to challenge them. For now, there was only the long flight home, the engine's steady rhythm, the fuel gauges creeping toward empty, and the knowledge that they had done what military doctrine said couldn't be done. They had brought single-engine fighters to Tokyo and back. Tomorrow, they would do it again. June 1944. Nakajima Aircraft Company's Ota plant, Gunma Prefecture, Japan. Assembly line supervisor Takeshi Yamamoto watched as workers fitted the 18th cylinder onto a HA-45 engine destined for a Ki-84 Hayate fighter. The engine that emerged from this factory should have produced 1,970 horsepower at takeoff, enough to propel Japan's most advanced fighter to speeds competitive with anything the Americans flew. Should have. The reality that Yamamoto witnessed daily told a different story. The steel arriving at his plant contained impurities that made proper heat treatment impossible. The aluminum alloys lacked the consistency that precision engine work demanded. The workers, many of them teenagers conscripted from technical schools after experienced machinists were drafted for military service, struggled with tolerances their training hadn't prepared them to achieve. The HA-45 engine represented Japan's most ambitious attempt to match American power plant technology. Its 18 cylinders, arranged in 2 rows of 9, fuel injection system, and single-stage 2-speed supercharger with water methanol injection, theoretically delivered performance that looked impressive on specification sheets. The engine's design incorporated lessons learned from years of air combat, addressing the power deficits that had plagued earlier Japanese fighters. On paper, the HA-45 produced 1,800 to 2,000 horsepower, depending on variant, figures that approached the Packard V1650-7 powering the P-51D. The gap between specification and reality widened with each passing month. Engines that tested at 1,900 horsepower under controlled conditions produced 1,600 horsepower or less when installed in operational aircraft. Some engines failed catastrophically within 50 hours of operation, their crankshafts snapping, their cylinder heads cracking, their supercharger impellers disintegrating at the precise moments pilots needed maximum power. The quality control systems that might have caught defective components before installation had collapsed under bombing, personnel shortages, and the desperate acceleration of production schedules that prioritized quantity over reliability. The Nakajima Ki-84 Hayate that emerged from Japanese factories in 1944 and 1945 embodied both the empire's technological ambitions and its industrial limitations. Designated Frank by Allied intelligence, the aircraft represented Japan's most serious attempt to counter American air superiority, with a fighter that could match Mustangs and Thunderbolts in speed, climb rate, and firepower. The specifications that greeted Allied technical intelligence teams appeared genuinely threatening. Maximum speed of 392 miles per hour at 20,000 feet, with some sources claiming 427 miles per hour under ideal conditions with high-octane fuel. Service ceiling of 34,500 feet. Rate of climb of 3,800 feet per minute. Armament of two 20mm HO-5 cannons and two 12.7mm HO-103 machine guns, with provisions for replacing the machine guns with additional 20mm weapons or even 30mm HO-155 cannons. These numbers suggested an aircraft that could challenge American fighters on roughly equal terms. Japanese aviation engineers had studied captured P-51Bs and P-47Ds, identifying the characteristics that made American fighters dominant and incorporating countermeasures into the Ki-84 design. The aircraft featured self-sealing fuel tanks, armor protection for the pilot, and a robust airframe designed to absorb battle damage that would destroy lighter Japanese fighters. The armored seatback alone weighed over 13 millimeters thick, a weight penalty that earlier Japanese designs had refused to accept. The Ki-84 represented a philosophical shift in Japanese fighter design, acknowledging that pilot survival mattered as much as raw performance. The problem was that Japanese industry in 1944 could no longer build the aircraft its engineers designed. Each Ki-84 rolling off assembly lines at Ota, Utsunomiya, and Manshu carried the accumulated deficiencies of an industrial base under systematic destruction. The high-strength steel required for landing gear struts arrived with carbon content varying by as much as 15% between batches. Heat treatment processes that should have hardened components to precise specifications produced inconsistent results, leaving some parts too brittle and others too soft. Landing gear that should have absorbed the shock of carrier-style landings on rough airfields instead collapsed without warning, destroying aircraft and killing pilots in accidents that never appeared in combat statistics. The fuel situation revealed the strategic catastrophe facing Japanese aviation with mathematical precision. The HA-45 engine was designed to operate on 100-octane aviation gasoline, the same high-performance fuel that American engines consumed in unlimited quantities. By mid-1944, Japan's access to such fuel had effectively ended. Allied submarines had severed the supply lines from Southeast Asian refineries. American bombing had destroyed domestic refining capacity. The synthetic fuel plants that German technology had helped establish couldn't produce sufficient quantities to maintain operations. Japanese aviation fuel quality deteriorated progressively throughout 1944 and into 1945. Fuel that tested at 92 octane in January might test at 87 octane by June, the refineries cutting corners to maintain volume. Some batches arrived at airfields testing below 85 octane, fuel that caused the HA-45's high-compression cylinders to detonate prematurely, destroying engines from within. Pilots reported engines that ran rough at any power setting, that produced alarming vibrations during climbs, that simply quit during combat maneuvers when fuel starvation or detonation damage overwhelmed weakened components. The aircraft that specification sheets claimed could reach 392 miles per hour struggled to exceed 350 miles per hour on the degraded fuel actually available at operational units. The desperation reached almost absurd proportions as Japanese military planners sought alternatives to conventional aviation fuel. Programs emerged to extract fuel from pine tree roots, a process that required approximately 200 pine stumps to produce a single gallon of low-grade aviation fuel. The mathematics were hopeless, but the effort continued, conscripting labor to dig stumps across the Japanese countryside, while factories sat idle for lack of fuel to test the aircraft they produced. Some units experimented with alcohol distilled from sweet potatoes, sake production byproducts, and other organic sources that produced fuel technically capable of combustion, but wholly unsuited for high-performance engines. Pilots who flew on such fuels reported engines that barely started, that produced perhaps 60% of rated power, and that failed without warning when the improvised mixtures clogged fuel systems or caused detonation damage. The pilot training crisis compounded the equipment failures in ways that made Japanese air defense increasingly ineffective, regardless of aircraft quality. At the war's beginning, Japanese naval and army aviators represented an elite force whose training exceeded anything available to their opponents. A Japanese fighter pilot in 1941 typically accumulated 300 to 500 hours of flight time before entering combat, with extensive training in aerobatics, formation flying, gunnery, and tactics. These pilots had dominated the early air battles of the Pacific, their skill compensating for equipment limitations that would later prove fatal. By 1945, that elite had largely ceased to exist. 3 years of attrition over the Solomons, New Guinea, the Philippines, the Marianas, and in the defense of the home islands had consumed Japan's experienced pilots faster than the training system could replace them. The veterans who survived found themselves flying constantly, unable to rotate to training duties because no one could be spared from combat operations. When they died, as they inevitably did given the hours they flew and the odds they faced, their experience died with them. The institutional knowledge that should have been passed to replacement pilots vanished into the Pacific, or the wreckage of burning aircraft scattered across island airfields. The replacement pilots entering Japanese squadrons in 1944 and 1945 received training that would have been considered grossly inadequate for a civilian pilot's license in America. Flight time before assignment to operational units dropped from hundreds of hours to fewer than 100, sometimes as few as 30 or 40 hours. Gunnery training, which required ammunition that couldn't be spared, was reduced or eliminated entirely. Formation flying, instrument navigation, and tactical maneuvering were taught from manuals rather than practiced in aircraft. Pilots arrived at their squadrons having never fired their aircraft's weapons, never flown in bad weather, never practiced the maneuvers they would need to survive combat. Captain Yasuhiko Kuroe, a Ki-84 pilot with the 85th Sentai who survived the war, described the replacement pilots who arrived at his unit in early 1945. They could barely keep formation in clear weather. If clouds appeared, they scattered like sparrows. Most had never fired their guns at any target. They knew the theory of aerial combat from diagrams and lectures, but had never experienced what it felt like to pull G's in a tight turn, to track a moving target through a gun sight, to maintain situational awareness while someone was trying to kill them. We tried to train them between missions, but there was never enough fuel, never enough time. Most died on their first or second combat mission. Some died in landing accidents before they ever faced the enemy. The contrast with American pilot training was devastating and grew more pronounced as the war continued. American pilots arriving in the Pacific Theater in 1945 typically possessed 400 to 600 hours of total flight time before entering combat zones. This included 70 to 100 hours in their assigned aircraft type, dozens of hours of gunnery practice against towed sleeves and camera gun exercises, and extensive training in instrument flying, navigation, and formation tactics. They had practiced combat maneuvers against experienced instructors flying captured enemy aircraft or accurate simulations, learning the capabilities and limitations of Japanese fighters before encountering them over the target. The training infrastructure supporting this system dwarfed anything Japan could maintain. American flight schools operated across the continental United States, in Canada, and at forward bases throughout the Pacific, producing 30,000 pilots annually by 1945. Each training base had dedicated aircraft, fuel supplies, ammunition for gunnery practice, and instructors who rotated from combat units to pass along current tactical knowledge. The pipeline operated with industrial efficiency, feeding a steady stream of competent pilots to combat squadrons, while maintaining quality standards that Japanese training had abandoned out of necessity. The armament comparison revealed another dimension of the technological gap that statistics alone couldn't fully capture. The Ki-84's standard armament of two 20mm HO-5 cannons and two 12.7mm HO-103 machine guns appeared formidable on paper. The 20mm rounds delivered devastating damage on impact, capable of destroying an aircraft with a single well-placed hit. Some Ki-84 variants replaced the machine guns with additional 20mm weapons or mounted 30mm HO-155 cannons for attacking heavy bombers. The firepower should have been sufficient to challenge any American aircraft. The reality of Japanese armament effectiveness told a different story. Ammunition supplies by 1945 had become so constrained that pilots were instructed to conserve rounds for only the most certain shots. The Ki-84's 20mm cannons carried 150 rounds per gun. The 12.7mm machine guns 250 rounds per gun, for a total of 800 rounds, less than half the P-51D's ammunition load. The 30mm cannons, when fitted, carried only 50 rounds per gun, giving perhaps 3 seconds of firing time before ammunition exhaustion. Japanese pilots had to make every shot count because there were no shots to spare. The ballistic characteristics of Japanese weapons created additional challenges that training might have overcome, but that inexperienced pilots found insurmountable. The 20mm and 12.7mm rounds followed different trajectories, converging at different ranges, requiring pilots to estimate which weapon would strike the target at any given distance. The 30mm rounds, much heavier and slower, dropped even more dramatically over distance. An American pilot with 6 identical 50 caliber machine guns harmonized to converge at 300 yards knew exactly where his rounds would strike. A Japanese pilot with mixed armament had to calculate mentally which of his weapons would be effective at any given range, a task that proved nearly impossible in the chaos of combat. The maintenance situation at Japanese operational bases had deteriorated to crisis levels that made even serviceable aircraft unreliable. The Ki-84's HA-45 engine required maintenance procedures and specialized tools that forward bases often lacked. Changing spark plugs, adjusting valve timing, replacing worn components, tasks that American ground crews performed routinely with standardized equipment, became major undertakings for Japanese maintenance personnel working with improvised tools and substitute parts. Aircraft that needed minor repairs sat grounded for days or weeks, awaiting components that might never arrive. The operational readiness rates that Allied intelligence estimated at 40% or below reflected not just battle damage, but the accumulated failures of a logistics system that could no longer support modern aircraft. Serviceable rates at some Japanese units dropped below 20% in the final months of the war. An interceptor group that nominally possessed 30 aircraft might have 6 or 8 actually capable of flight on any given day. The others sat in revetments with missing engines, collapsed landing gear, inoperable weapons, or any of dozens of other deficiencies that the maintenance infrastructure couldn't address. Mechanics cannibalized parts from damaged aircraft to keep others flying, but even this expedient failed when the supply of aircraft to cannibalize ran out faster than replacements arrived. The production numbers that seemed impressive on Japanese military reports masked the reality of aircraft that couldn't fight. Nakajima delivered approximately 3,514 Ki-84s before the war ended, a significant number by Japanese standards, but representing perhaps 2 months of American P-51 production. Of those 3,514 aircraft, significant percentages were destroyed on the ground, American bombing before ever flying a combat mission. Others were lost in training accidents that reflected pilot inexperience and aircraft unreliability. Many sat grounded at airfields across Japan, awaiting fuel that would never come, parts that didn't exist, or pilots to fly them. The American production advantage operated on a scale that Japanese planners found incomprehensible. North American Aviation's factories in Inglewood, California, and Dallas, Texas, produced P-51 Mustangs at rates that exceeded Japan's entire fighter production across all types. At peak production, a new Mustang rolled off the assembly line approximately every hour, more aircraft per day than Japan produced Ki-84s per month. By war's end, North American had delivered 15,586 P-51s of all variants, with the D model alone accounting for 8,156 aircraft. This single aircraft type, from a single manufacturer, exceeded Japan's total production of all fighter aircraft in the final 2 years of the war. The quality control that American production maintained at these volumes would have seemed impossible to Japanese manufacturing supervisors struggling with inconsistent materials and undertrained workers. Each P-51D that left the assembly line was essentially identical to every other, built to tolerances that ensured interchangeable parts and predictable performance. A pilot could climb into any P-51D anywhere in the world and know exactly how it would fly, exactly where every control and instrument would be located, exactly what performance to expect. Japanese aircraft, increasingly hand-built with variable quality materials, showed performance variations of 20% or more within the same production batch. A Ki-84 that could achieve 380 miles per hour might come from the same factory as one that struggled to reach 340 miles per hour. The difference traceable to manufacturing variations that quality control systems could no longer catch. The strategic implications of this production disparity extended beyond simple numbers to reshape how each nation approached air warfare. American commanders planned operations knowing that aircraft losses could be replaced within days. Mechanical failures that grounded aircraft could be repaired with standardized parts shipped from continental depots. Pilots who completed their combat tours could be rotated home, their experience preserved for training the next generation. The system operated with redundancy built into every element, accepting losses that would have crippled Japanese operations as routine overhead. Japanese commanders faced the opposite reality. Every aircraft lost was effectively irreplaceable, the production system unable to keep pace with attrition. Every pilot killed took months of training to replace, assuming fuel and aircraft for training were available, which they increasingly were not. The mathematics of attrition that had worked against Japan since Midway accelerated catastrophically in 1945. Each month's losses exceeding the previous months, while replacement capacity declined. Lieutenant Commander Yoshiro Hashiguchi, operations officer for a Ki-84 unit based at Matsuyama, documented the situation in reports that survive in Japanese military archives. In April, we had 24 pilots and 30 aircraft. By May, we had 18 pilots and 22 aircraft. By June, we had 11 pilots and 14 aircraft. We were receiving 2 or 3 replacement pilots monthly, teenagers who needed 6 months of training we couldn't provide. We were receiving perhaps 1 replacement aircraft per week, and half of those had defects that grounded them immediately. We could calculate exactly when our unit would cease to exist as a fighting force. The mathematics were precise and inescapable. The Ki-84 Hayate represented everything Japanese aviation engineering could achieve by 1944. Its design incorporated lessons from years of combat, protection for pilots that earlier Japanese philosophy had rejected, performance specifications that approached Western fighters, and armament that could destroy bombers with well-placed shots. Under ideal conditions, with experienced pilots, 100-octane fuel, and proper maintenance, the Ki-84 was a formidable opponent that demanded respect from American pilots who encountered it. But ideal conditions had ceased to exist for Japanese aviation. The pilots were undertrained, the fuel was degraded, the maintenance was inadequate, the replacement parts were unavailable. The production quantities were insufficient. Each element of the system that should have supported the Ki-84 in combat had failed or was failing, transforming a theoretically competitive fighter into what American pilots increasingly called easy prey. The aircraft that Japanese designers created on drawing boards in 1942 and 1943 bore little relationship to the aircraft that Japanese pilots flew in 1945. The gap between specification and reality, between design intent and manufacturing capability, between theoretical performance and operational effectiveness grew wider with each passing month. American fighters flying over Tokyo in April 1945 encountered not the Ki-84 of specification sheets, but the Ki-84 of industrial collapse. Underpowered, poorly maintained, flown by pilots who had never had the opportunity to learn their trade. The shock that Japanese pilots experienced upon encountering P-51 Mustangs over their homeland reflected not just surprise at American range capabilities, but recognition of a technological and industrial gap that no amount of courage could overcome. They flew aircraft that their factories could barely build, powered by engines that their refineries couldn't fuel, maintained by ground crews who lacked tools and parts, into combat against opponents who possessed everything in abundance. The Ki-84 Hayate, Japan's last hope for air defense, had become a symbol not of what Japanese aviation could achieve, but of what Japanese industry could no longer deliver. June 1st, 1945. Somewhere over the Pacific Ocean, 400 miles north of Iwo Jima, Captain Robert Moore of the 78th Fighter Squadron watched his artificial horizon tumble uselessly as his P-51D entered a towering cumulus formation that wasn't supposed to exist. Weather briefings that morning had promised clear skies along the return route from Osaka. Instead, the 150 Mustangs of the 15th and 21st Fighter Groups had flown directly into a frontal system that stretched from sea level to 40,000 feet. A wall of violent turbulence, zero visibility, and ice that turned aircraft into coffins within minutes. Moore's cockpit filled with the electric blue glow of St. Elmo's fire, dancing across his canopy and wing surfaces. His compass spun in directions that bore no relationship to actual headings. The aircraft bucked and shuddered through updrafts and downdrafts that exceeded anything his training had prepared him to survive. Somewhere in the churning gray void around him, 91 other pilots fought the same battle against weather that killed more efficiently than any Japanese interceptor. Black Friday, as the Mustang pilots would call it afterward, claimed 27 aircraft in minutes. Of those losses, 24 resulted not from enemy action, but from weather alone. Pilots becoming disoriented in instrument conditions they couldn't escape. Aircraft colliding in clouds where visibility dropped to zero. Engines failing as carburetor ice formed faster than heating systems could prevent. Fuel exhaustion as pilots circled desperately seeking clear air that didn't exist. The disaster demonstrated that even American technological superiority had limits, that the very long-range missions pushed men and machines to edges where nature could still kill with impunity. The losses of June 1st represented the worst single-day attrition the VLR fighter force would suffer throughout the campaign. Yet the missions continued the following day, and the day after, and every day that weather permitted, until Japan's surrender. The American system could absorb catastrophic losses and continue operating. The Japanese system could not. This asymmetry, more than any single engagement or tactical victory, defined the air war over Japan in its final months. The operational rhythm that emerged from Iwo Jima between April and August 1945 created a grinding attrition that Japanese air defense could not sustain. On days when weather cooperated, approximately 100 P-51Ds would depart the volcanic island's airfields, their Merlin engines warming in the pre-dawn darkness, their pilots consuming coffee and Benzedrine to sharpen reflexes for the 8-hour ordeal ahead. Each aircraft carried 269 gallons of internal fuel, plus two 110-gallon drop tanks, a total of 489 gallons that would be consumed almost entirely before the distinctive cone of Mount Suribachi appeared on the horizon again. The mathematics of these missions revealed the industrial infrastructure required to maintain such operations. A single mission of 100 aircraft consumed approximately 48,900 gallons of 100-octane aviation fuel, accounting for combat maneuvering that increased consumption above cruise rates. Armament loads totaled roughly 188,000 rounds of 50-caliber ammunition, each round manufactured in plants across the American Midwest and shipped across 5,000 miles of ocean to reach the volcanic rock where armorers loaded belts in the tropical heat. Oxygen supplies, hydraulic fluid, engine oil, spare parts, food for ground crews, medical supplies for casualties. The logistics chain stretched back across the Pacific to factories, refineries, and farms that operated around the clock to feed the war machine. Behind the fighters came the aircraft that made their missions possible. Liberty ships arrived at Iwo Jima's improvised harbor daily, their holds packed with the materiel that modern air warfare consumed at rates that would have bankrupted any other nation. Fuel tankers brought aviation gasoline refined in Texas and California, shipped through the Panama Canal or around Cape Horn, transferred to smaller vessels for the final approach to beaches that still contained Japanese holdouts in caves. Ammunition ships carried explosive cargo across submarine-infested waters, their crews knowing that a single torpedo hit would produce an explosion visible for 50 miles. Transport aircraft flew regular routes from Hawaii and the Marianas, delivering high-priority items that couldn't wait for surface transport. Engine parts, instruments, medical supplies, and the 1,000 small items that kept an air force operational. The Japanese logistics situation had collapsed into desperate improvisation that could sustain neither offensive operations nor effective defense. Aviation fuel reserves in the home islands had fallen below 200,000 gallons by August 1945, less than what the Iwo Jima Mustangs consumed in 4 days of operations. The fuel that remained was allocated primarily to kamikaze aircraft, the strategic calculation being that suicide attacks offered better returns per gallon than conventional fighter defense. Interceptor units received fuel allotments that permitted perhaps 2 or 3 sorties per aircraft per week, assuming the aircraft were otherwise operational, which many were not. The ammunition situation proved equally dire. Japanese arsenals had shifted production toward anti-aircraft shells and ground defense weapons as the prospect of American invasion grew more certain. Fighter ammunition competed with artillery shells, naval weapons, and small arms for manufacturing capacity that shrank monthly under American bombing. Pilots received strict instructions to conserve ammunition, to fire only at targets they were certain to hit, to break off engagements rather than expend rounds in uncertain combat. The pilots who might have developed marksmanship through practice had no ammunition to practice with. The pilots who entered combat had no ammunition to waste learning deflection, shooting under fire. American intelligence monitored the collapse through signals intercepts, aerial reconnaissance, and the reports of submarines patrolling Japanese waters. Photo interpreters studying images of Japanese airfields documented the progressive paralysis. Aircraft lined up in revetments with no fuel in their tanks. Maintenance crews cannibalizing parts from damaged aircraft to keep others flying. Dispersal patterns that indicated fear of attack, but no capability to mount defense. The reconnaissance pilots who flew specially modified P-51Ds over Japan reported airfields that intelligence listed as containing hundreds of aircraft, but that actually held perhaps a dozen operational machines, surrounded by derelicts stripped of engines, propellers, and anything else that could be removed. Lieutenant Colonel John Mitchell, who had led the mission that killed Admiral Yamamoto in 1943 and now commanded fighter operations at Iwo Jima, analyzed the Japanese response patterns with growing confidence. Their interceptions are becoming sporadic and uncoordinated. We'll encounter heavy opposition on one mission and nothing on the next 3. They're clearly husbanding resources, but they don't have enough resources to husband. Every time they commit fighters, they lose fighters they can't replace. Every time they don't commit, we bomb their factories and airfields with impunity. They're trapped in a losing equation. The exchange ratios documented this losing equation with statistical precision. The April 7th mission had produced kills claimed at approximately 21-2, better than 10-1. Subsequent missions improved on this ratio as American pilots gained experience over Japan, and Japanese pilot quality continued its fatal decline. By June, individual missions were producing kill ratios of 15-1 or 20-1. By July, some engagements saw American fighters destroy Japanese aircraft at ratios approaching 30-1. The few Japanese interceptors that rose to challenge them, piloted by teenagers who had never experienced combat before and would never experience it again. The cumulative statistics told the story of systematic destruction. Between April and August 1945, P-51 Mustangs operating from Iwo Jima were credited with 206 Japanese aircraft destroyed in aerial combat. Approximately 75% of all Pacific Theater P-51 aerial victories. The actual number was certainly higher, as many Japanese aircraft shot down over the home islands were never confirmed, their wreckage lost in forests, mountains, or urban areas that couldn't be surveyed. American losses during the same period totaled 85 pilots killed on VLR missions, but only a handful of these, perhaps 5 or 6, died in aerial combat. The remainder succumbed to weather, mechanical failure, navigation errors, or the accumulated exhaustion of missions that pushed human endurance beyond its limits. The psychological impact on Japanese forces compounded the material destruction. Pilots who survived encounters with American formations returned to their bases with reports that commanders found difficult to believe and impossible to counter. Captain Teruo Kawanishi, a Ki-84 pilot with the 73rd Sentai, who survived 3 engagements with P-51s over the course of the campaign, described the hopelessness in post-war interviews. "We would climb to intercept, burning fuel we couldn't replace, and find ourselves facing formations we couldn't defeat. The Americans flew with complete confidence, as if they knew exactly what we would do before we did it. They would dive through our formations, fire short bursts, and zoom climb before we could react. Our aircraft couldn't match their speed in the dive or their climb rate at altitude. We were target practice for them." The technological advantage that American pilots enjoyed in combat extended beyond airframe and engine performance to encompass every system that supported modern air warfare. The G-suits that American pilots wore, inflating automatically to prevent blood from pooling in their lower extremities during high-G maneuvers, permitted aggressive combat maneuvering that would have caused Japanese pilots to black out. American oxygen systems functioned reliably at altitudes where Japanese systems frequently failed, producing hypoxia that slowed reactions and clouded judgment at precisely the moments when clarity meant survival. The VHF radios in American cockpits provided clear communication on multiple channels, enabling the formation coordination that Japanese pilots, often flying without working radios, couldn't match. The rescue infrastructure that supported American operations provided psychological benefits that transformed how pilots approached risk. Along the route between Iwo Jima and Japan, submarines designated for lifeguard duty patrolled specific stations, their positions known to pilots who could ditch near them with reasonable hope of rescue. PBY Catalina flying boats, nicknamed Dumbos, flew search patterns looking for downed airmen, their crews trained in open-ocean rescue techniques. American pilots who went down over water had realistic chances of survival, not guaranteed, but possible enough to remove the fatalism that characterized Japanese operations. Japanese pilots possessed no such infrastructure. A pilot forced down over water was effectively dead, his life raft, if he had one, often defective, his emergency rations consumed during ground shortages, his chances of rescue essentially zero. The submarines that might have rescued him were on the ocean floor, sunk by American anti-submarine warfare. The flying boats that might have searched for him didn't exist in numbers sufficient to cover the vast Pacific. Japanese pilots flew each mission as if it would be their last, because, statistically, it very well might be. The final aerial combats over Japan revealed the complete collapse of Japanese air power as an organized force capable of defending the home islands. August 10th, 1945. The same day that Japanese leadership debated acceptance of the Potsdam Declaration. P-51s of the 15th and 506th Fighter Groups encountered Japanese interceptors near Tokyo in what would prove one of the last significant aerial engagements of the war. The American fighters claimed 7 Japanese aircraft destroyed at no loss, a ratio that, by this point, surprised no one. The Japanese response was so weak, the interception so poorly coordinated, that American pilots reported feeling something approaching pity for opponents who rose to fight, despite knowing they could not win. 4 days later, on August 14, 1945, August 15th in Japan due to the international date line, Lieutenant Jerry Yellen of the 78th Fighter Squadron flew what would become the last American combat mission of World War II. Taking off from Iwo Jima with his wingman, 2nd Lieutenant Philip Schlamberg, Yellen led a strafing attack against airfields near Nagoya. The mission had been planned before word of Japan's imminent surrender reached Iwo Jima, and the recall code word, Utah, that would have aborted the attack, never reached the pilots' radios. Or if it reached them, came too late. Yellen and Schlamberg completed their strafing runs against a Japanese airfield, their .50 caliber rounds tearing through parked aircraft and ground installations. Anti-aircraft fire rose to meet them, the Japanese gunners firing with determination that the Emperor's recorded surrender announcement, already broadcast but not yet universally known, had not diminished. The 2 Mustangs banked into a cloud formation to escape the ground fire, a standard evasive maneuver practiced hundreds of times. When Yellen emerged from the clouds, Schlamberg was gone. The 19-year-old lieutenant from New York had been hit by anti-aircraft fire and crashed somewhere in the Japanese countryside, becoming the last American combat death of World War II. The war had ended. The Emperor had already recorded his surrender announcement. Yet Japanese guns still fired, and American pilots still died. The machinery of war taking hours to wind down, even after the political decision to stop had been made. Schlamberg had survived dozens of missions over Japan, only to die after the war was effectively over, a casualty of the gap between strategic decisions and tactical reality. Yellen returned to Iwo Jima alone, landing as the sun set over the Pacific. Within hours, word of Japan's surrender reached the island, and the missions stopped. The Mustangs that had terrorized Japanese airspace for 4 months sat silent on their hard stands, their guns unfired, their fuel tanks full. Their pilots suddenly uncertain what to do with themselves now that the purpose that had defined their existence had ended. The strategic assessment that emerged from the VLR campaign confirmed what the daily statistics had suggested throughout. American air power had rendered Japanese air defense irrelevant months before the atomic bombs fell on Hiroshima and Nagasaki. The B-29 superfortresses that carried those weapons flew without fighter escort, not because escort was unavailable, but because it was unnecessary. Japanese interceptor opposition had been so thoroughly destroyed, so completely overwhelmed, that bombers could penetrate Japanese airspace with near impunity, regardless of their target or their altitude. The production statistics that supported this dominance continued to widen even as the war ended. American factories had built 15,586 P-51 Mustangs of all variants, more than Japan produced of all fighter types in 1944 and 1945 combined. Production rates at North American Aviation's plants had reached 20 aircraft per day, more P-51s per day than Japan built Ki-84s per month. The Japanese aviation industry that had produced competitive aircraft in 1941 and 1942 had collapsed under the weight of bombing, blockade, and the accumulating disadvantages of fighting an industrial war against an opponent with unlimited resources. The pilot training disparities that had opened in 1943 had become an unbridgeable chasm by 1945. American training programs produced 30,000 pilots annually, each receiving 200 to 300 hours of instruction before assignment to combat units. Japanese training had essentially stopped. The fuel and aircraft required for instruction consumed by operational demands that took priority over developing future capability. The few replacement pilots who reached Japanese squadrons possessed neither the skills nor the confidence to challenge American dominance. Fuel consumption revealed the final asymmetry with mathematical clarity. The VLR missions from Iwo Jima consumed approximately 60,000 gallons of 100-octane aviation fuel per day for fighter operations alone. B-29 operations, transport flights, reconnaissance missions, and support aircraft pushed total daily consumption into hundreds of thousands of gallons. American tankers delivered millions of gallons monthly to Pacific bases, a river of fuel flowing across the ocean from refineries that operated at capacity. Japan's entire remaining aviation fuel reserve, the strategic stockpile upon which home defense depended, had fallen below 200,000 gallons. The mathematical comparison was stark. America consumed Japan's entire remaining fuel supply every 3 to 4 days of normal operations. The empire that had gone to war partly to secure oil resources was reduced to extracting fuel from pine stumps, while American tankers delivered petroleum in quantities that Japanese logistics officers found incomprehensible. The human cost of the campaign distributed unevenly between the combatants, reflecting the technological and industrial disparities that had defined the conflict. 85 American pilots died on VLR missions between April and August 1945, most from operational causes rather than enemy action. Japanese pilot losses during the same period numbered in the hundreds, possibly exceeding 1,000, with entire squadrons eliminated in futile attempts to challenge American formations. The 47th Sentai, which began April with 40 operational pilots, had 3 remaining by August. The 244th Sentai was destroyed, reformed with replacement pilots, and destroyed again. Unit after unit suffered the same fate, fed into a battle of attrition they could not win against an opponent who could replace losses while they could not. General Curtis LeMay, commanding 21st Bomber Command, offered an assessment that captured the strategic reality. The fighter escorts made the B-29 campaign possible. They swept the Japanese Air Force from the sky. By July, we could bomb Japan in daylight with minimal losses, because there was nothing left to oppose us. The Japanese had pilots, and they had aircraft, but they couldn't put the two together in sufficient numbers to matter. We had won the air war completely. The surviving aircraft tell their own story across the decades that followed. Of the 3,514 Ki-84 Hayates produced, a single example survives today, preserved in the Chiran Peace Museum in Kagoshima, Japan. The aircraft sits in a hall dedicated to kamikaze pilots, a solitary reminder of Japan's final, desperate attempt to match American technological superiority. Its HA-45 engine is silent, its guns empty, its cockpit a memorial to pilots who flew knowing they would not return. Hundreds of P-51 Mustangs survive in museums and private collections worldwide, many of them still flying. At air shows across America and Europe, Merlins sing the song they first sang over Berlin and Tokyo, their distinctive sound recognizable to aviation enthusiasts who weren't born when the aircraft flew in combat. The disparity in survival rates reflects the disparity in production, in maintenance philosophy, in the fundamental approaches each nation took toward the machines that fought their wars. American aircraft were built to endure, maintained with care, preserved as artifacts of a victory that transformed the post-war world. Japanese aircraft were built for immediate use and expected destruction, their survival rate reflecting the strategic circumstances that produced them. The shock the Japanese pilots experienced upon encountering P-51 Mustangs over Tokyo in April 1945 was not merely tactical surprise at American range capabilities. It was recognition that the war had evolved beyond anything Japanese strategy had anticipated, that industrial capacity and technological innovation had overcome the geographical constraints that had protected Japan for centuries, that distance itself had been defeated by engineering, logistics, and the mathematics of total war. The pilots who climbed to meet those Mustangs flew into a battle they had already lost. The outcome determined in factories and oil fields and training bases, thousands of miles from the sacred airspace they were trying to defend. In the end, the P-51D Mustang over Mount Fuji embodied something larger than any single aircraft, or pilot, or mission. It represented the culmination of a way of war that prioritized industrial capacity over individual heroism, technological superiority over martial spirit, logistics over tactics. The laminar flow wing that reduced drag by 35%, the Merlin engine that maintained power at altitudes where Japanese engines gasped, the training programs that produced competent pilots by the tens of thousands, the supply chains that delivered fuel, ammunition, and spare parts across oceanic distances. Each element combined to create a military capability that Japanese forces simply could not match. The very long-range missions from Iwo Jima to Tokyo demonstrated that in modern industrial warfare, victory belongs not to the side with the bravest pilots or the most elegant aircraft designs, but to the nation that can sustain operations indefinitely while its opponent exhausts its resources. American forces could absorb losses, replace aircraft, train new pilots, and maintain the tempo of operations regardless of casualties. Japanese forces could do none of these things. The mathematics of attrition, visible in every mission report and every kill ratio and every fuel consumption statistic, had determined the war's outcome long before the atomic bombs fell. When the guns finally fell silent in August 1945, the P-51 Mustangs at Iwo Jima represented the sharp edge of a military system that had proven itself capable of projecting overwhelming force across distances that previous generations had considered unconquerable. The pilots who flew those aircraft had accomplished what military doctrine said couldn't be done. They had brought single-engine fighters to Tokyo and back, sustained operations for months, and destroyed Japanese air power so thoroughly that the final bombing missions flew without opposition. The Japanese commanders who had dismissed American logistics capacity, who had calculated culminating points based on European precedent, who had believed that distance would protect the homeland, learned the hardest lesson of modern warfare. They had prepared for everything except the industrial might that could put fighters over Tokyo from bases 750 miles away, that could sustain such operations indefinitely, that could replace losses faster than Japanese forces could inflict them. The shock of American fighters over Mount Fuji was ultimately the shock of mathematical reality asserting itself against strategic assumptions that the mathematics had already disproven. The Mustangs had done their job with the ruthless efficiency that characterized American military operations in 1945. They had proven that distance was no defense, that industrial might trumped warrior spirit, and that technological superiority, properly applied, was insurmountable. The age of the samurai had ended over the sacred airspace of Japan itself, replaced by the age of the production line, the supercharger, and the very long-range fighter escort. Divine wind had been conquered by science, the warrior spirit broken by industrial might, and the empire of the rising sun overshadowed by wings of aluminum and engines of steel.